Hi and welcome to this second video on hypothesis test. In the first video we looked at the principles of hypothesis testing. We went through all the terminology and the ideas behind it. In this one we're going to have a look at a few examples and actually carry out some hypothesis tests. And what I've done is use this PowerPoint as a way to just kind of get a few grievances off my chest, a few kind of arguments bits and pieces that really bug me. So the first one is this one. We've probably all seen adverts for shampoos or whatever it is, and you see the little bits in small print at the bottom where they say, yeah, kind of the hair has been volumized, as if we can actually kind of somehow calculate the volume of hair. No idea how to do that, but basically what we're saying is you always get that small print at the bottom that says, if you look out for it in adverts, the sample of people that they took and how many people actually said yes, they agreed with the manufacturer's claims. Now, so what we've got is a company that manufactures shampoo claims 90% of the people can tell their hair has been volumized. So they take a sample of 20 people, which 15 say they can distinguish the remarkable volumizing properties. Is the manufacturer's claim correct at the 5% level? Is it possible that 90% of people say yes, they can actually tell that this product works? So here we go. I suspect you know which way this is going to go, but there you go. Right, the null hypothesis is that H0, the probability that somebody can tell is 0.9, and the alternative hypothesis is that the probability is actually less than 0.9. So what we're going to do first of all is we've got to determine, is this a one-tail or two-tail test? And because we're looking at strictly less than 0.9, that tells us we are looking at a one-tail test. So let's now set up our binomial. So we've got 20 people, 20 trials, probability of success 0.9, probability that somebody can tell it's 0.9. And what we're going to do is we want to know is this value of 15, is this significant or not? So what we're going to do is we're going to calculate the probability that we get equal to or less than 15 people. And given the fact that we've got 90% of people say that they can tell the difference, is getting 15 or less, is that likely or is it too unlikely? And so what we're going to do is plug that into the calculator and it gives us a value of 0.043. Now what we've got to do is do a comparison with our 5% level, and clearly we can see that the likelihood of getting 15 or less with a 0.9 or a 90% figure is actually very unlikely. It's 0.043, 4.3%, which is less than our 5% level. So what we're saying is the result that we got, this 15 people say they can distinguish it, is actually really unlikely if 90% of the people could tell. So what that's telling us is that the 0.43 is in the critical region, so x equal less than 15 is in the critical region, so we are going to reject our null hypothesis and we're going to accept the alternative hypothesis, which is that in actual fact it's actually far less likely that you can tell. So what we're saying there is the manufacturer's claim is not supported at the 5% level, and again that statement at the end is linked back to the original claim or the context. So again, what we've got there is not a massive amount of maths, and the marks in the exam will be for, first of all, will be for setting up your null hypothesis, alternative hypothesis. The next one will be kind of stating clearly that we've got a one-tailed test, doing the comparison, getting the right figure, and then finally coming up with the claim at the end. So you're looking at probably 4 marks, which the actual maths of it is just that statement, and then you can get that off your calculator. So it's all about the interpretation of what's going on rather than actually number crunching. Okay. So that's our first example done. Here's our second one. This one, I've had many an argument, well, I say many an argument, I've had a long argument in the pub about this one, and a number of times people say, oh, do you put the milk in first or you put the milk in afterwards and it makes a difference to the taste, and all that kind of stuff. You've probably had that argument yourself. You're either going to be a pre-milker or a post-milker when it comes to your tea. So what we've got is Terry and June are having an argument about tea. Terry says it makes the tea taste worse if you put the milk in before the hot water. June says it doesn't. Terry says he can tell the difference, so they set up a test. Right, out of 15 cups, Terry gets 10 correct, and can we tell the difference at the 10% significance level? So here we go. We've got to set up our hypotheses first of all, then we've got to do the calculation, and then we've got to do comparison against the 10% level. So here we go with the hypothesis. So, if it's not possible to tell, then you've basically got a random 50-50 chance of getting it right. So straight away we can say our null hypothesis is that H0, the probability of getting it right is 0.5, and if Terry can tell the difference, then his probability of getting it right would actually be higher. So what we've got to do is check against our binomial distribution, which is 15 cups of tea, probability of success 0.5. So what we're going to do is our probability actually greater than 0.5? So what we need to do is check about the calculation and say, well, is it going to be 10 or more? And so the probability of Terry getting 10 or more correct, which would lead us to accepting the alternative hypothesis, put that into your calculator. You're going to have to do a 1 minus, which is that, and that gives us 1 minus that figure, which gives us 0.15. So what we're saying is the probability of Terry getting 10 or more correct is actually 15%, given the fact that it was 0.5, i.e. he couldn't tell the difference. And being as we're comparing this with the 10% level, we're saying that this 15% is within our acceptable region. It's not, Terry getting 10 is not statistically significant. It's not unlikely enough. So what we're going to do is accept our figure that we're using, which is the 0.5. We're going to accept 80. And so we're saying there's not enough evidence at the 10% level to suggest Terry can actually tell the difference. Okay. In both those two previous examples, we've just done a test and we've kind of done a comparison of our probability against a given region. What we're going to do is kind of turn that around a little bit in this next example. So what we've got is a teacher thinks 65% of students at college meet the deadlines for their homework, and she selects 28 students at random. It says calculate the values for the critical region of the two-tailed test. So we're turning this around slightly. And we're also given the piece of information to say that the tail for each test should be as near to 2.5% as possible. So here we go. We've got a binomial. It's 28 people. The probability that they meet the deadline for their homework is 0.65. And what we've got to do is have a look at a two-tailed test. So we're looking at both ends. So what we're going to do now is start calculating figures to find our values that are closest to this 2.5%. So what we've got is H0 is the probability 0.65 and H1 probability not 0.65, hence our two-tailed test. And let's start having a look at some figures. So we need to know some value x below which it's actually less than 2.5% and some other value at the top end such that the probability of getting greater than that is it's also less than 2.5%. So here we go. Let's just start banging some numbers into the calculator. It says use tables. As I mentioned in previous videos, you can find tables of binomial figures in your formula booklet. But the easiest thing to do is just to whack them into the calculator, and so you've just got to kind of start guesstimating and trying to find figures that work. And so if I do the probability that x equal less than 13, I actually get a value of 0.0336, which is fairly close to 0.025, but let's see if we can get even closer. I want this probability to be lower, so I need to go more towards the end, so I need to pick a value less than 13, so let's go for 12. So there it is, and that's 0.013, so clearly 0.025 is somewhere in between those two. So we're going to be one of these two at the lower end. And at the upper end, this is where I've got to start doing some 1 minuses. So for x greater than equal to or greater than 23, we want equal less than 22, gives us that figure, nearly 4%. And so I need to go closer to the tail, so I need to go up one from there. So x equal to greater than 24, which is 1 minus probably x equal less than 23, which gives us this 0.13 figure. Okay, so we know that the values we're looking for is kind of sandwiched in between 12 and 13, sandwiched in between 23 and 24. So let's have a little bit of a close look at those. It says the probability for each tail should be as near to 2.5% as possible. So we've got to decide which of these figures here is closest to 0.025. And if you think, well, kind of going from 25 to 33 compared from 13 to 25, as it turns out that one is actually a bit closer. And on this side, again, it's this one here that's a bit closer. So those are my two values that are closest to the 0.025 figure. So what that tells me is I've now identified values for my critical region. And at the 5% level, my critical region is therefore x equal less than 12 or x equal to or greater than 24. So if we had a test statistic, we'd be comparing it against these two numbers. Right, on we go. We've got our two values, and part B says calculate the actual significance level. Now we're testing it at 5% level, but clearly we saw from the previous slide, it's not possible to get the figures to work out to be exactly 5%, so what is our significance level? Well, those are our two figures, and so basically what we're saying, if we just put those two numbers together, what we've got, the actual significance level, is actually 2.772%. So it's actually nowhere near the 5% level, and that's just because of the way that the numbers have worked out. So what we've got is a significance level that's actually a lot harsher than the 5% we were asking for, but it's the best we can do with the numbers as they are. Right, and then finally on to part C. She took a sample, 25% of students who met the deadline. Let's comment on this in relation to the hypothesis test. So we've got 25 students met the deadline. 25 is in the critical region because it's bigger than 24. So it's in the critical region, so that means we reject H0. We're going to accept H1. So there is evidence, yes, the proportion of students meeting deadline is actually higher than 65%. And there we go, hypothesis testing done. Like I say, it may be that you oh my word, I've not got a clue what's going on, but I promise you, once you start having a go at a few questions and start getting your head around them, you'll realise that they're very kind of structured, very kind of do the same each time. So set up your test, H0, H1, decide one-tailed test, two-tailed test, bang the numbers into a calculator, do a comparison, link it back to the context. That's essentially what you're doing. And once you get the hang of them, they're actually not as bad as you might think.